Hello and welcome to this lecture. We are now going to talk about a very interesting model where you use two continuous random variables or multiple continuous random variables and think of them as being jointly distributed and jointly continuous. Okay, so this is a very important model. I'll motivate it with some data from the irises, but you'll see that in many typical situations this model can be very useful. So what once again in this course we'll focus on is how to write down the distribution under these models, how to do computations with them. The skill of computing with them is very important. We'll build up that skill in this part of the lecture. Okay, so jointly continuous random variables is the topic. Okay, so to motivate it, let's look at pictures here. I've drawn a couple of 2D histograms. Okay, so previously we saw 1D histogram, right, one-dimensional histogram, where a lot of data is available. We bin them into suitable intervals and make a plot, that bar chart kind of plot, and that's how we moved into the continuous random variable situation, right? We made a histogram and we observed that there is a nice smooth shape for this histogram. So let's go and use that shape as the density, and that simplified our calculations, and we use that model quite extensively. So far we've been using it for computations. Now we'll push that into multiple dimensions. Okay, so for that the motivation is to look at two-dimensional histograms. What are two-dimensional histograms? What I've shown here in the blue picture on the left is a 2D histogram for the sepal length and the sepal width together in an iris. Okay, so we had all this data which had for every row there was a sepal length and a sepal width, right? So now we can do two-dimensional binning. What is two-dimensional binning? How many of these sepal lengths and sepal widths fall into a rectangle? Okay, they are between, let's say, 4.5 and 4.6 and 3.7 and 3.8. Okay, how many of them are there? Okay, I'll share some code with you later on the Colab notebook on how to make these kind of plots. These kind of plots are very interesting, right? They look like a big city, laid out in some detail on the ground. Of course, our cities are not so planned as this one, but anyway, so this looks like a very planned city. So this is how to make these plots. You'll see, I'll show you some methods later on. But what do we learn from this plot, right? So what we learn from this plot is there is a joint distribution between the sepal length and the sepal width. Okay, so clearly this joint distribution is plotted out here, right? Some of the lengths, right? So some of the lengths are possible, some of the length and widths are possible in some combination, not possible in some other combination, right? So that's what this is showing you. When you have those peaks, those tall buildings, means in that place a lot of sepal lengths and sepal widths fall. But there are blanks, right? So just one blue, just like a flat thing on the ground, nothing rising. So in those regions it won't fall. Okay, so these are, to whatever extent you have data, you can come up with plots like this. Okay, the same thing I've done on the right in the green plot for petal length and petal width. Okay, so petal length and petal width and sepal length and sepal width. We have both 2D histograms. Once you see the 2D histogram, it's clear to you that they are jointly distributed in some way. Okay, so that's the first thing. So notice what's going on here. So both this sepal length and sepal width, I want to model as continuous random variable, right? That's what makes most sense from the data. It seems to make some sense. And now they have a joint distribution. Okay, the same story goes for the petal length and petal width also. Okay, so now we need tools. We need descriptions of jointly continuous random variables, two random variables which are continuous and they have a joint distribution. How will you describe that? Okay, so just before we saw a discrete and a continuous random variable having a joint distribution, and we learnt about how to deal with that. Now we are dealing with two continuous random variables and how to deal with that. Okay, and this is the motivation. So clearly it's well motivated from random phenomenon that you observe in practice, and many more such phenomena you can see. And as you grow more in data science, you will face these situations often. Okay, so how do we deal with it in probability? This is the idea. The idea is to use something called a joint density. Okay, so if you remember, go back to the discrete random variables we studied. When we want to study multiple discrete random variables together, we use the joint PMF, right? And the joint PMF plays the very crucial role of understanding what the distribution is going to be and all that. Okay, so likewise here, when you want to study two continuous random variables, you have to use something called the joint density. Okay, so joint density is a function of two variables. Okay, so a lot of people say A function of one variable is already a headache. Now you're giving us two headaches at the same time. Yes, it is a little bit more complicated. You have to deal with both of these variables, understand them, do calculations with them, differentiation, integration, all of that will enter the picture. It is a little bit confusing, but if you take your time with it and spend some time with it, you'll see it's good to appreciate situations where two random phenomena and two variables are sort of linked, and how do you picture that mathematically, how do you model that. Joint density is a indispensable tool. Okay, so a joint density function is much like a PDF. We had a density function, right? It had some properties. It needed to be non-negative, has to integrate to 1. Something very similar you want for a function of two variables, f of x, y. It has to be non-negative. That's one condition. The other condition is it has to integrate to 1 over the two-dimensional plane. So now there's two variables, so you can do two direction integrals. Okay, so this is multi-directional integral. When you do that big integral, you should get 1. It should just all integrate to 1. There is a technical continuity requirement, which we will sort of assume in this class at least, piecewise continuous in each variable. Okay, so first two are critical. It needs to be non-negative and it should integrate to 1. Okay, so that's the definition of joint density. You can see how this very easily extends from one dimension, right? In one dimension also you have something very similar. We extend it to two dimensions. Okay, so technically, so this point is just to get rid of the probability space and all that. It turns out once you have a joint density, there are two random variables which have a joint which live in some probability space, so that so notice this equation is very important. You identify any region in the two-dimensional plane, okay, and you say what's the probability that x and y jointly will fall in that region. Okay, so maybe it's a circle, maybe it's a rectangle, on the 2D plane you just draw some region. What's the probability that both my random variables will take values, so that x and y together, when you plot x comma y, you will go into that region. Okay, so this is a question you can ask, a very reasonable question, right? What is the probability that both of them will lie together? What is the probability that the sepal length and sepal width will be within 4, let's say, right? So it's a very reasonable question to ask, and that probability is obtained by integrating the joint density over that area, over that region. Okay, so this is easily one of the most important formula involving density. Go back to the one-dimensional, one random variable situation, right? When you have one continuous random variable, how do you find probability of the random variable falling inside a certain interval? You simply integrate the density over that interval. Same thing you do here. You integrate the density over the region, you get the probability. Okay, so that's why it's the density. It's like the probability per unit area, sort of. This f of x, y is like that, per small little area. So you integrate it over the area, you get your actual probability. So that's why it's called the probability density. Okay, all right. So a quick word on notation. It's very common in many books. You will find when f of x, y is thought of as a joint density of x and y, people will use the notation f subscript x, y. Okay. Now this x, y is a little confusing. A lot of people will think it is x times y. Okay. Maybe you want to write capital X comma capital Y, but nobody writes that comma. Okay. It's sort of implicit from this, and you have to get used to that notation. Okay, so joint distribution, joint density has this kind of notation, f sub xy of x comma y. So this, when you write f x y of x comma y, it's immediately clear what it is, right? So you don't have to say it's the joint density, etc., etc. So that's why this notation is very useful. One very important thing that we had, even in one continuous random variable, is the support of that random variable, right? The support was all the points where the density was strictly greater than 0. Same thing we can do here, except now the support will be two dimensions. It will not be one dimension, right? It's not just one line. It's over the plane wherever the f of xy is non-negative. I mean, not non-negative, strictly positive. It's greater than 0. It cannot be equal to 0. That part is the place where the random variables jointly take values, right? So they take values there. So it's called the support of the random variables x comma y. Okay, a whole bunch of definitions. Hopefully in the next slide we'll see some more examples and see how to work with. Okay, so here's the simplest example of a joint density, a very commonly used joint density, very popular, so you should get to know, understand and how to use this. Okay, so let's picture this. It's good to plot it. I mean, it's two-dimensional plots. Three-dimensional plots are very difficult, but what I like to do is to plot the 2D plane and show the support and sort of visualize the 3D thing as coming out of the 2D plane in different ways. Okay, so here is what you can do for the support. You have x here, y here. So notice this density fxy of x comma y is 1 for x between 0 and 1 and y between 0 and 1. Okay, so x is 0, x is 1 here. Let's say y is 0, y is 1 here. So the support is inside this unit square. Okay. Okay. So it's good to draw a region like this and shade it like this, right? So you just draw these shading lines sort of. So you get the support. So this is the support of xy. Okay. So if you want to picture sort of in your mind, if you want to picture the 3D plot of the joint density, how will it be? It will be like this, one square block that comes up to a height of 1, and it is right, it's a cube that's sitting there on that support, right? So that's how this function fxy of x comma y will look if you want to plot the value in the z axis. Okay, you need 3 axes, no? Because there is already 2 variables, and then the third function value itself will go on the third axis. So it will be a picture like that. So picture that in your mind. Anytime you have a function like this, always try to make a mental picture of how it will look on the 2D plane and how it will come up. Okay, and that will give you a lot of clarity. Okay, so now remember what we said in the previous thing. So supposing I define a region A, right? So let me define a region A. So okay, so first let's test the integration. So this integration, so first of all, this fxy is a valid density, right? It's non-negative, it's greater than or equal to 0, that we can see. And if you integrate over the whole thing, you don't have to integrate over the whole thing, it's enough if you integrate from 0 to 1, 0 to 1, 1 dx dy, you will simply get 1. You can check that's what it will be, right? So you first do this integral, it's x between 0 and 1, that's just 1, and then again you do integration over y, you will get 1. Is that okay? So think about how this integration works. It's a little bit difficult if you're seeing it for the first time, but hopefully you do the x integration first, right? So maybe I should write that down. So this is the x integration that comes first. Okay. So the y integration. So one integral of 1 is simply x, right? X going from 0 to 1, and then dy still remains. This guy is just equal to 1. So you get integral 0 to 1, 1 dy, and then that is again y 0 to 1, that's 1. Okay, so this is how you do it, sort of laboriously one at a time. So multiple integrations is just a sequence of integrations. There's nothing special about it. You first do the integral over x, treating everything else as constant, right? So when you do the integral over x, there is no everything else here, everything else is just 1, so it's no big deal. But usually you'll see, some integrals can have something more fancy here, but just treat it as a single integral, right? So integral 0 to 1, 1 dx, this is just x, no? From the formula you know that if you differentiate x, you get 1, right? So you put x, between 0 and 1, it's just a definite integral, so you just get 1. So it's just 1 dy, now integral 0 to 1, 1 dy, it's easy to do. So it's just 2 simple one-dimensional integrals. Okay, so we have checked that this is a valid density. Okay, the next thing was about integrating to find probability, right? So supposing you have a region A here, right? Some region A here. Okay, so now the probability of x comma y falling in this A is equal to integral over A 1 dx dy. This is nothing but the area of A. Okay, so you can see it comes out to be simply the area of A. So if you want to find the probability of A, you simply find its area. Whatever shape it may be, you find its area. So for instance, if A is, you do half here and then half here, supposing that is your A. So probability that 0 less than x less than half and 0 less than y less than half, this is the area of the smaller square, and that's just half into half, it's 1 by 4. Okay, so why did it become the area? Because of this 1. Okay, so it was just uniform, so it just becomes 1. Okay, it becomes the area. So it's just 1 here, and it's the unit square. So in the unit square, so when you have the unit square uniform in the unit square, probability of any region inside the unit square is simply its area. Okay, so it's very easy to remember. This is one of the simplest joint densities you can have. Very few practical models will exactly fit this, but it's good to know that there are easy joint densities of this fashion. Okay, so as we go along, we'll see slightly more complicated examples of how to do probabilities and all that, and I'll walk you through these integrations a little bit more slowly, but hopefully you see the big picture of where it is, right? So how do you generalize this now? If you want to go to an arbitrary joint density, there will be some region in the 2D plane where that density will take value. And if you want to take probability of a region inside that support, you simply integrate the density over that area, you will get it. Okay, so that's the probability that you have to find. Okay, so this is how you deal with joint densities. Okay, all right. So here are a whole bunch of problems that have been asked around this joint density. So whenever I have a problem like this, I always like to picture it in the 2D plane and then try and solve it. So look at the first one. What is the probability that x needs to lie between 0 and 1 and y should be in 0 and 0.1, 0 and 0.1, 0 and 0.1. So if you want to draw it, let me see how to draw it in as least painful as possible. Okay, so I might have to make multiple pictures like this, excuse me for that. So here is one, so this is the full support, and this is asking for 0.1, 0.1, right? And x has to be between 0.1, 0.1, so this is the area that we are interested in. So this area is just 0.01, isn't it? So this guy is 0.01, okay? And next there is the other area, 0.5 to 0.6 and 0 to 0.1. So maybe I'll change the color, okay? 0.5, x is between 0.5 and 0.6. Okay, I don't know how many colors I can do here, so maybe I should erase this. Okay, so that's 0.01, it's black in color. And then y is between 0 and 0.1. So y is between 0 and 0.1, so it will lie in this thing. Okay, so you see here y, this area, this blue area is x lying between 0.5 and 0.6 and y lying between 0 and 0.1. And what is the area? The area still remains the same, right? It's 0.1 into 0.1, it's 0.01. Okay, so the probability that x and y together lie in this area is 0.01. And the last one, maybe I should change my color to some green here. So x is between 0.9 and 1 and 0.9 and 1. So that will come, I don't know, somewhere here. Okay, so that's 0.9, 0.9 and 1, 0.9 here. So here also, if you were to do the calculation, it's going to be 0.1 into 0.1, it's 0.01. Okay. The next calculation that's being asked here is x between 0 and 0.1. That's it. Nothing on y. X is between 0 and 0.1. So how do we do this? So let me draw one more set of axes for this. That will help, I think. 0, 1 and 1 here. Let's draw it off. It says x has to be between 0 and 0.1. So x is between 0 and 0.1. I don't care what y is. So then you take the entire range of y. Y can be anything, but x is between 0 and 0.1. Okay, so what will be this area? It's just the area of this rectangle. Length is 1, width is 0.1. So it is 1 into 0.1. That's just 0.1. Okay. The next question asks for y. Let's go to the blue color. Y between 0.5 and 0.6. So y is between 0.5 and 0.6. It's probably much smaller than this, but anyway, I'm just drawing like that. Okay, so y is between 0.5 and 0.6. I don't really care what x is. So it's this whole area. Okay, so this will also come out as 1 into 0.1, which is 0.1. Do you see that? Do you see how for the uniform and the unit square, it's just a question of sketching that region and then simply finding its area. Okay, so now we have more involved things. So let me draw one more picture here. So notice, so it's just a question of I'm trying to specify this area A in more and more complicated fashion. The first two examples, I simply gave ranges of x, ranges of y, so you could simply draw it. So now I'm saying probability that x is greater than y. So how do you draw x greater than y? So maybe I should draw it here. 0, 1, 0, 1. For x greater than y, you should first draw the x equal to y line. Okay, so this is the x equal to y line. Okay, and this is 1 comma 1, remember. So what is the range of values where x is greater than y? It's this area, isn't it? Okay, so now we have a triangle. Okay, so probability x greater than y is the area of this triangle, and that's half into base into height, and that's half. Okay, so that's easy to do. Here is the next problem where x is greater than 2y. Okay, again we just draw the same method. You just draw this for the uniform, the unit square. It's very easy. You just take the picture here and then do it. So I need x equals 2 times y. So it will be a line like this, right? So this will go to, okay, it's not to scale, but hopefully you see it. So this is x equals 2y, and then I need the area of this. So that's going to be half into base into height, which is 1 by 4. Okay, and finally I have a x squared plus y squared is less than 0.25, right? 0.25 you know is 0.5 squared. So this from your experience you may know is actually a circle, right? It's going to be a circle. It's going to be a circle with radius 0.5. Okay, so it will be like this. It will be a circle like this. I'm sure I can draw the circle properly. There you go. It's roughly okay. So it's half. Okay, and it's a circle, and this is like 1/4 of a circle, right? So it's 1/4 times pi times r squared. So that will be pi by 16. So that's the formula. That's the answer for this this probability. What's the probability that x squared plus y squared is less than 0.25? It's pi by 16. Okay, so notice we're dealing with numbers like pi and all. That's really great. Okay, so I know, I mean, if you're not sure about this formula, if you didn't know it's from a circle, etc., and area of a circle is pi r square, etc. So go back and check out how you describe circles involving x and y. Okay, so that's half, that's correct. Okay, so hopefully uniform in the unit square, you'll be very comfortable doing computations of probability given any area. You'll be able to just find that area and write it down. Okay, so one can also do some integral formula for this, but I'm not doing it right now. We'll do slowly later on when we need it. Okay, so that's the first step of example. Okay, so now I'm going to talk about the general 2D uniform distribution. Okay, so previously we had the uniform distribution only in the unit square, right? Just in the unit square we had a uniform distribution, and we were able to easily do it. Now we can extend. Instead of having the support as the unit square, you can have any reasonable two-dimensional area. Okay, I put reasonable in bracket, just say any region, it's okay, it's for our purposes, it's good enough. So any two-dimensional region that you can think of and you can plot and sketch, etc., you can simply imagine two random variables x, y having the uniform density on that region. That region could be many possibilities. So here are some possibilities I've drawn here. The first one says it's a rectangle, right? So it can be a rectangle between x taking values between AB and y taking values between CD. I'm drawing it on the positive side. It can be anywhere. Just for convenience, I'm drawing it. This can be the support, right? So this is the rectangle we're talking about between x between A and B and y between C and D. It can be a circle. Okay, so that's the equation of a circle centered at x naught, y naught. Okay, this is the equation, and it's a circle of radius r. Okay, so of course I'm drawing it very poorly out of scale. So this is the circle here, and you can even have multiple disjoint regions. So what do I mean by that? I might draw, I might draw one rectangle here, another circle here, and some other bizarre shape here, and say my xy is uniform in this support. Okay, so just say all these things. So you find the total area. Okay, see D is what? D is the total area of all these regions together, and my density will be 1 by the total area in these regions wherever you are inside. Whenever you are inside this region, it's 1 by that area. Whenever you are outside this region, there is no support, it's 0. Okay, density goes to 0. Okay. So this kind of a picture is very important. So sometimes when you observe two random variables which you think are continuous, you draw their histogram, 2D histogram, and you notice it's roughly of the same height in one area. A good model is to say, in one area or multiple areas like that, a good model is to say uniform in that area, okay, or a starting model, why not, right? So it's a good thing to think of. So this is the 2D uniform distribution. A very easy density is just 1 by the total area of support that you are having, okay. All right. So the formula for any sub-region now is very easy for the uniform distribution. You have, instead of the unit square, supposing you have an arbitrary region D and you define a sub-region A. What's the probability that xy falls inside that sub-region? Is simply the ratio of the two areas. Area of A divided by area of D. Okay, so area I am showing with absolute value symbol. You can use other notations if you like. So it's basically area of A divided by area of D. Okay, so that's the thing to think of. Because it's uniform, this works out. Okay, so if you have a flat histogram without too much variation, roughly flat, then uniform is a very good model to use. Okay, so I have a couple of problems more. Let's just quickly work through these problems, and that will conclude this lecture on continuous random variables, jointly continuous random variables. Okay, so here I've defined a more complicated looking region D, and I'm saying x and y are uniform in that. I want you to sketch the support and compute probabilities of two areas. Very basic problem, important skill to pick up. At least with uniform distributions, you should be able to pick up this skill. Given a region, just sort of describe that region mathematically, sketch it, and then compute some areas. Very simple description. Maybe pictorially you can do, but sometimes being able to do the calculation is very important, and that's a very good skill to have in general. Okay, so let's sketch this. So the sketch is important. It's x greater than 0, y greater than 0, right? So I like to draw it like this. X is greater than 0, y is greater than 0, and x plus y is less than 2. So I need to draw x plus y equal to 2, and that will be a line like this. Oops, it will be very symmetric. Okay, so that's the line. So this is 2, and this is your support. This line is x plus y equal to 2. Okay, so that's the line. And what is your fx of xy? Is if fx of fxy of xy is going to be 1 by the area. What is the area? This area is total area is half into base into height, 2 into 2, that's 2. Okay, so it's going to be half for x comma y in D, okay, which is this triangular area, and 0 otherwise. Okay, so this is the density function. All right, so that's good to know. So the total area is 2, so we are seeing that. Now probability of x plus y less than 1. So how do you get x plus y less than 1? That is just 1 here. Okay, so you can draw this line. That line will be x plus y equal to 1. Okay, so the area inside this guy. So this area is half into 1 into 1, and that's just half, right? So what's the probability that x plus y is less than 1? That is just half divided by 2, that's 1 by 4, right? So the total area is 2, this area is half by 2 is 1 by 4. See, that's the nice thing about uniform distribution. You don't have to do any integration. It is just area calculation. If it's simple enough calculation, you can do it. The next one is x plus 2y greater than 1. Let me do the blue calculation here. This may get a little bit more complicated. So x plus 2y equal to 1. So where is that line going to lie? X plus 2y is equal to 1. So it will have, it will start at 1. It will go up to half here, I think this is the line. Okay, so when y is 0, x is going to be equal to 1, right? And when x is 0, y is going to be equal to a half, and I want x plus 2y greater than 1. So it's going to be all this area. right? This area is this, x plus 2y greater than 1. Okay, so how do you find the area in blue? The area in blue is best found by the blue area equals the overall area, which is 2 minus the small triangular area, right? So, it is half into 1 into half. So, it is 2 minus 1 by 4, and that is what? 7 by 4. Okay, that is the blue area. So, probability that x plus 2y is greater than 1 is 7 by 4 divided by 2, that is 7 by 8. So, quite a high probability that x plus 2y becomes greater than 1. So, you notice how I did this. Since it's just uniform and you only have straight lines separating the regions, it's easy to just simply find the area and then divide the areas to get the probabilities that you will lie inside a smaller region. Okay, so this works for uniform, doesn't work for non-uniform. Okay, so uniform is very, very easy. Okay, so next example we are going to see is a non-uniform density. This is the first time ever we are seeing a non-uniform density. So let's spend a little bit of time understanding what it is. So this is the density. The function that's given to you is fxy of x comma y equals x plus y. Notice it's not 1 divided by the area or something. It's x plus y for x lying between 0 and 1. Okay. So you have to show that the above is a valid density. Okay. The first thing you can check is that fxy is greater than or equal to 0. Right. X and y are between 0 and 1. And x plus y is definitely positive, it's greater than or equal to 0. The slightly difficult thing is to check is the integration, right? So, x and y is between 0 and 1. I always like to plot the support. So, let me just do this. It's easy to check fxy is greater than or equal to 0. And if you were to plot the support is between 0 and 1. This is the support, but the density is not uniform in this, right? So, density is sort of like a 3-dimensional picture, right? So, if you want to try to picture the 3-dimensional one, x plus y, when x and y are 0, x plus y is equal to 0. When x and y are 1, x plus y is equal to 2. So, it sort of goes like an inclined plane from 0, 0 to 2, comma 2, okay? And when x is 1 and y is 0, it is at 1. And likewise on the y-axis also it's at 1. So, it is sort of like an strange inclined sort of plane going in a different direction. Okay. So, it's hard to picture. You can try plotting it in 3 dimensions in Python or something, and you can picture it a little bit, but there's a limit to which you can picture these things in 3D. But it's good to have a mental picture in your mind that it is sort of starting at 0 and it's inclined. It's not flat, right? It goes up. So, x and y together are much more likely to lie close to 1, 1 than 0, 0. Okay, so that's the sort of density this is. So, density changes, suddenly you see dramatically everything seems to shift, right? So how do you show it's a valid density? You need to integrate. You integrate x from 0 to 1, y also from 0 to 1, right? So, there's no problem in that range. X plus y dx dy. Okay. So, let us look at the first integration, and in that integration I can treat y as a constant. Okay. Treat y as a constant. Y is like 2 or 3 or any number, constant, right, some c. Okay. So, if you have to do that integration, integral 0 to 1 x plus y dx. So, I can integrate this as first x and then y. So, what is the integral of x? It is x squared by 2, and y is a constant, so it will be just yx. So, this is the integration, and I have to substitute between 0 and 1. If you substitute 1, I get half plus y. If you substitute 0, I get 0, so it's half plus y. So, this entire inside integration becomes half plus y. So, now I go y equals 0 to 1, half plus y dy, and this is just a direct integration, right. So, half plus y dy is y by 2 plus y squared by 2 between 0 and 1, and that is just 1. Okay. So, this gives you a check that this is a valid 2-dimensional density, right. So, over 2 dimensions it needs to have a total integral of 1. Okay. So, this is sort of like the volume that is inside this region x plus y. Okay, so that's how we get this one. It's not a cube or anything, so it's not easy to compute the volume. So you have to do the integration carefully. Okay, so this is how you do it. Notice there's no major integration involved here. It's just you do the inner integral first, and then you do the outer integral. Just step by step, if you do, it will come out quite easily. Okay, hopefully this is not too scary. Okay, so now notice the probability here. The first probability asks you to find for this region half half. Okay, so for that region, I don't know if I have a working sheet or not, maybe not. Okay, so I should do it off right here. So for that region, so let me just maybe block it out. Oops. Okay, I'm just trying to demarcate an area where I don't know why it doesn't draw when I do this. Okay, I'm just trying to demarcate the area so that I can work on the other thing. So I'm going to do probability that x is less than half and y is less than half. So if you notice, this is the region and I have to integrate over that region, right? So 0 to half, 0 to half, and then x plus y, just the same density dx dy. Okay, so I do the same integration. So the inside integration goes first. So I retain the outside integration. I'm not going to touch it now. The inside integration x plus y, remember y is treated as a constant. So the integral will just become x squared by 2 plus yx substituted between 0 and half. And this whole thing I will integrate out with y. So this is sort of, you can see how I'm writing. I'm collapsing the steps that I had before. I'm treating that whole integral inside and then finishing it off. Okay, so this integral, if you put half, I'm going to get 1 by 8 plus y by 2. Okay, and that I have to integrate between 0 and half. Okay, once again the integral is going to be y by 8 plus y squared by 4, 0 and a half. So that will be 1 by 16 plus 1 by 16, that's 2 by 16, 1 by 8. So you see, notice how x and y are likely to take higher values together. They're between 0 and half and 0 and half, it's only 1 by 8 probability. Okay, so that's the way in which the sloping goes. It starts at 0, so lower values are taken with much lesser probability than higher values. Okay, so this clearly brings out that non-uniform nature in this thing. So if it were to be equal, it will be just 1 by 4, isn't it? It should be 1 by 4, it's gone to 1 by 8, much lower probability that it takes lesser values. Notice the next one is a bit of a pain. It says probability that x plus y is less than 1. So let's do blue color here. So x plus y is less than 1 is this blue area. Okay, so this guy is x plus y equal to 1. So now if I want to set up probability that x plus y is less than 1, you'll see you'll run into some problems when you want to set up a double integral like this. Okay, so setting up a double integral like this needs some care. Okay, so I have x here, y here, and I have this x plus y less than 1, and I want to integrate only from here to here. Okay, so the way I usually try to do is I try to keep the outside integral as the y integral, and the outside integral will go from y equals 0 to 1. Okay, so if you look at, just forget about the x-axis at all, forget that the x-axis even exists. Okay, on the y-axis I go from 0 to 1, right? So the first integral can go from 0 to 1. Now fix one particular value of y. Okay, so now when you enter the second integral and you look at the range of values of x, you have to fix a particular value of y and then just draw a line parallel to that and see where it hits the boundaries. On the one side it's at 0, so x equal to 0. Where does it hit the boundary on the other side? Okay, so this point will be 1 minus y comma y, right? Because that line is x plus y equal to y, x plus y equal to 1. So if y is y, x will be 1 minus y. So it hits the boundary on one side at x equal to 0, on the other side at x equal to 1 minus y. Okay, so this part is one of the trickiest parts in two-dimensional integration. Okay, how to set up the limits for the integral to get a particular area. So in this case I wanted this area x plus y less than 1. You draw this triangle and then slowly set up the axis one at a time, limits one at a time. How do you do that? You first start with one of these things, y going from 0 to 1, and then you fix a particular value for y and then go into the next one. And then when you fix a particular value of y, draw a line parallel to the x-axis, see where all it hits boundaries. There are two boundaries here in this region, and it hits the first boundary at x equal to 0, the second boundary at 1 minus 5. You simply integrate from 0 to 1 minus y. Okay, everything else remains the same, x plus y dx dy. Okay, all right. So hopefully you see this. So this one now, I'll keep the outer integral 0 to 1. The inner integral is going to be x squared by 2 plus yx. By now you should be familiar with this. I'm doing 1 minus y dy. So now I have to substitute this here. So it will be 1 minus y whole squared plus y into 1 minus y by 2 plus y into 1 minus y. Okay. So one needs to simplify this. So let's do that. Okay. So you will get 1 by 2 times 1 minus 2y plus y squared plus y minus y squared, the whole thing dy. So, right, so this is what you got here, and that will work out as integral 0 to 1, the constant term is half, minus y plus y will cancel, right. So, the y term will disappear, we will have a plus y squared by 2 minus y squared, this will be minus y squared by 2 dy. So, now we are in familiar territory. This is just y by 2 minus y cube by 6 between 0 and 1, and that is just half minus 1 by 6, which is 1 by 3. Okay. So, that is calculation. It took some time and effort, but look at the nice result it gave you, right. So, it's the support is 0 1 0 1, support is the unit square, but it is non-uniform. So, if you take half the area, right, if you divide the area into 2 and if you take half the area, you actually get a probability of 1 by 3. Okay. So, that again shows you how non-uniform this distribution is. Okay. So, this calculation is considered a basic skill in this area. When you study two-dimensional continuous densities, joint densities, you're given the density description and then you're given a sub-area description. You should be able to quickly set up an integral and do the calculation. And this, as far as this course is concerned, we won't ask you very difficult integration or anything like that. Even this integration, I would say, ranks as slightly more difficult than what I would like. But at least you should be able to set up a numerical algorithm to compute this integration. Okay, so even if you cannot do it by hand, doing it by hand maybe is a good skill. If you can have it, it's great, but you can't, you should be at least able to set up a computer to give you the value of the numerical double integration. If you can do that, that's fine. Okay, so hopefully this problem was useful for you. Okay, so that concludes the study of joint densities. We saw uniform densities. We saw one example of a non-uniform density. We'll see many more examples as we go along. But there are a few skills here to pick up. Given a description of the density, how to draw the support, how to do some calculations of probability, etc. Important skill. Okay, and also equally important is given data, given a 2D histogram, how to think of where the support may be, what kind of distribution fits this, what kind of continuous distribution fits it. That's also a very useful skill to develop. Okay. Thank you very much. I'll meet you in the next lecture.